Hello there, Year 9. Welcome back to the last half term of this school year. Very important half term, obviously, because you are going to be Year 10s next year, but we're working well and we're going to do great stuff. Hopefully you all had a lovely break and a lovely rest over half term. Got some sun, but not too much. Remember how quickly you can burn. We've got an interesting little topic now, electricity in the home. There would normally be some practicals we do at school, but might be a bit tricky to do those at home, but hopefully I found a way of making it interesting anyway. Being really kind for you today, saying you do now is to find the new page in your knowledge organiser for your new topic. It is only one page for electricity in the home, but you have got a couple of diagrams that you need to learn. If you cannot find your knowledge organiser and you haven't found it yet on Teams, let me know and I'll make sure you get a copy. So there we go. And slightly cheesy, but I had to put in a picture of Greece. It's electrifying. That was a good old summer movie. Made you feel good. If you want to watch it, why not have a go? So you've got some objectives today. Of course, you have got 8 keywords to look out for during this presentation. You need to find out how they are used, what they mean, be able to explain them appropriately yourself. 2 key ones are alternating current, which is sometimes called AC, direct current, sometimes called DC. The others are wires and parts of plugs. You have got you need to know the parts of the national grid, you need to know the features of home wiring, and you are going to be doing a treasure hunt to find features in your home. You will need to take pictures, label them, and submit it through to me on Teams. So, 2 types of current basically. A current here for electricity has an E in it. Easy to remember, E for electricity, E for current. If you put an A in it, it's a dried fruit, a dried grape. It will not be appropriate, it will not conduct electricity. If you have a battery powered circuit, for example, you've got a torch you take out at night when it gets dark, you've got a battery working it, then in that case the current just flows in a loop. It's a direct current, it will only flow in one direction. Yes, I've got my favourite joke in there. Yeah, I know you will all have missed it. However, when you are at home, the lights in your home will work on mains electricity. They don't all have batteries in. And this repeatedly changes direction. It changes from positive to negative, back to positive, and back to negative, positive, negative, positive, negative. You've got the idea because it changes from opposites. It's called an alternating current. It's alternating between being positive and negative. The frequency of the current is the number of cycles per second. That's the number of times it changes. And the mains frequency in the UK is 50 cycles a second, which is also called 50 hertz. And hertz is abbreviated as a capital H and a small z. Now there is a graph to go with this. I know you will be pleased. So you've got the voltage along the y-axis. You have got time passing along the x-axis. Obviously time doesn't need to stop, but we don't want to have a ridiculously stupid graph. And as you can see, the current slowly builds up to a maximum positive charge, and then it decreases through the 0 point to a maximum negative charge. And the maximum positive and the maximum negative have the same value. Yeah, and this is what you get down your live wire in your home, the current. Now, the maximum positive is 325 volts. The maximum negative is 325 volts. So the total difference between them, the potential difference, is 650 volts. 325 from here down to 0, and another 325 in the opposite direction down to the minimum here. And it's because you have such a large potential difference that live wires are very dangerous. This is why we are not going to have you doing wiring practicals at home. Your neutral wire in your house goes all the way back to the substation, and it is earth there. You may see substations when you're out and about for a walk, that's something you could add to your checklist. Now you do need to be able to label this graph and explain it. It's not too tricky, it's just something I'm afraid you have to learn. Here we go, next bit now. The national grid. This is how the electricity gets from where it is generated to your home. So you have a power station. The power station can be fired by coal, it can be fired by gas, it can be fired by nuclear reactions. We have covered all of this during our energy unit earlier this year, and it produces about 25,000 volts of potential difference, a very high charge, very dangerous. When it is leaving the power station to go to these things here that are meant to look like electricity pylons, you get something called a step up transformer. Easy to remember, step up, because that actually concentrates the power. It increases it to 132,000 volts. Yeah, so it's really compressive, make it really large potential difference here, and that is why you don't want to be messing with your power cables on your pylons. Now obviously as it gets closer to your house, you don't want to have 132,000 volts coming into your house. It would blow your appliances at home. So what we have instead, sorry about that guys, is a step down transformer, and a step down transformer reduces the voltage down to around 230 volts for homes and offices, and that includes schools as well. Factories will get a larger supply because they are likely to have machines that will need more current to run, and by having the potential difference really large here at the national grid, you don't need so much current to actually transfer the same amount of power. And if you use less current, then it makes it more efficient because less energy is used in the transfer and more of it gets to the home. And if we're going to be generating carbon dioxide burning gas and coal, we don't want to be wasting a lot of the energy we have used. Remember, you will have had equations in the past for useful energy and wasted energy. If you're not sure, go back and revise those. Now we're coming to what you see in your house: plugs, sockets and cables. Now you can see the plugs, sockets and cables externally in your house. What you can't see is you have also got loads and loads of cables running inside your walls, all connected up in a really big circuit. We have done circuits before and you know how they work. They can be in series, they can be in parallel. They're inside your walls. That is why if you are doing DIY at home and you're likely to be drilling, you're advised to use a cable checker first to make sure that you don't drill through a piece of plasterboard into an electric cable and damage yourself and your appliances. So the bits that you can handle, the bits you can see, when you have plugs, sockets and cables, the outer casings, the bits you touch, are made out of insulating materials to keep you safe. Even when they look like metal, they usually have plastic underneath. Most mains appliances are connected to the mains, that's the electricity cables in your house, using a 3-pin plug in the UK. You know that if you travel abroad, you've been to Europe in the past, you often have to have an adapter because they often only have a 2-pin plug. The earth wire and all the wall sockets connect to the ground and they do not carry a current. That's the longest pin in your plug. It's there to try and keep you safe. The pins are made of brass, which is a good conductor and will not rust. Now, if I hear you manically looking at your periodic table and thinking, Miss, help, I can't find brass, that is because brass is not an element. Brass is an alloy. It is a mixture or a compound of two different metals. And when you have a compound, it has a combination of two or more elements, and the properties of the compound are different from the original elements. And it's a good conductor, but it will not rust. We don't want rust actually reducing the size of pins in plugs and making them less safe. Plugs, if you can open them up, have a fuse. It's about 1 centimetre long. It's a little cylinder piece. You have to match the fuse to the appliance. They are a safety feature, because if too much current passes through it, the fuse will actually melt. People describe that as being blown. When that happens, the current will stop flowing and you are protected. Most plug appliances these days have molded on plugs, but you can still have a little space where you can pop a fuse in and out. You have 3 colours of wire in there. You have brown, which is live, blue, which is neutral, green and yellow stripes, which is connected to the earth pin. These colours are the same for all plugs in the UK. Those colours have been chosen because for people that have colour blindness, in other words, they are not able to differentiate between different colours easily, these are colours that do not get confused with each other, so you can still see them. And that is why the green and yellow is also striped, to make it easier to stick out. You will need to know these colours. There is a diagram in your knowledge organiser of a plug showing which cables go where. They always go to the same place. Makes it safe because you don't have to worry about what goes where. It's all universal, and you will need to learn that. Here comes your task. This is quite good fun, I think, actually. You've got a treasure hunt. Wow, Miss, love a treasure hunt. You are going to be taking photos of all these things, labelling them, see how many you can find. First of all, a wall socket, then a rocker switch, a pull switch, plug on an appliance which is wired directly to the mains without a plug, a room in your house that does not have wall sockets. You don't have to take a picture of the room, you can just identify that. Your fuse box, always good to know where it is. Do not touch it though, because there is a lot of electricity passing into there, and you do not want to damage yourself or to damage anything in your house. If you have got a parent or carer who is an electrician, I'm sure they will explain a lot more about all of this to you. You may have a PIR. These are clever devices which will they replace the switch and they will see movement, and they will use that to put lights on or off. If there is movement, the lights will go on. If there isn't movement, the lights will go off. They are also sensitive to the ambient light, so lights will only go on or off if it is dark. So they're actually a way of saving energy. You may have those. You may have, for example, a light outside on your drive which works on a PIR. A little bit of a big hint there, but aren't I kind? What safety features can you identify with these elements you will find around your home? Some of these are specifically related to safety. So you have got 1, 2, 3, 4, 5, 6, 7 that you'll definitely be able to find. The PIR is a bonus 8. So take photographs of them, make notes about what you notice about them, and submit it to me on Teams. This is the easy start to this. Next week's lesson will involve calculations, so you will need a calculator or the calculator feature from your laptop. Hoping you're all good. Obviously this will be on Go for Schools. It will be on Teams. If you can submit your work on assignments in Teams, it gives me a feedback box which is really easy to get a reply to you. If you really can't manage that, then please send the work through by email. But most of all, stay safe in the sun and stay distant from each other, but do not forget to send work to me. Take care. Speak to you soon. Bye.